Hello! In this video I'm going to go through two examples relating to finding the partial fraction decomposition of proper rational functions. So what I mean by proper in these cases, the degree of the numerator is greater than the degree of the denominator. So in the first case this has degree 1, whereas the denominator has degree 2, and here this is degree 2, or the denominator here will have actually degree 4. So both of these cases are proper rational functions. If you have an example that you need to solve where it is not proper, so the degree of the numerator is at least as big, equal or bigger than the degree of the denominator, then you would simply divide the denominator into the numerator and you would have a polynomial plus the remainder divided by, again, the denominator. And that second piece will be strictly proper. In these cases, I've avoided the polynomial division step by simply setting up problems where I can focus on the partial fractions themselves. Now, in the first case, we have 3x divided by x minus 1 times x plus 2. And so we need to set up the partial fraction decomposition. So a and b here are going to be some constants. But because we have two distinct linear factors, so this becomes a over x minus 1. And then the second is b over x plus 2. We'll see in the second example a repeated linear factor and an irreducible quadratic factor. So the task is to find a and b. And here this becomes relatively simple. Bring this again into a single rational expression, essentially trying to work out that these two are the same, so write them in the same way. So to do that, multiply this top and bottom by x plus 2. So we have a times x plus 2. This will be divided by the product x minus 1 and x plus 2. And then similarly in the second case, multiply top and bottom by x minus 1. So b x minus 1 divided by x minus 1 x plus 2, and that in turn is equal to a times x plus 2 plus b times x minus 1 all over x minus 1 x plus 2. So what that gives us is that if this rational expression is equal to this rational expression, then the numerators are equal because the denominators are equal. And so we have to solve a polynomial equation where we have 3x on the left is equal to a x plus 2 plus b times x minus 1. So one approach of doing this is to multiply out the right hand side. We get a linear expression. So we equate the coefficients of x, and then we equate the coefficients of, well, x to the 0. We equate the constants. So that will give us two equations in a and b, and that's enough information to solve. But actually, that's not the most straightforward thing we can do. So we take these two polynomials. If they're the same polynomial, then evaluating at the same point will give me the same value. So we have 2 points which become very useful. So if we say that x is equal to minus 2, x plus 2 becomes 0. So we simply ignore this and we're left with an expression that involves b only. So at x is equal to minus 2, what we get is minus 6 on the left is equal to a times 0, just so I have a record of it, plus b times, and this will be a factor of minus 3, so minus 2 minus 1. And so that tells me minus 3b is minus 6, so that b is equal to 2. And then similarly, I can make this factor go away if I evaluate everything at x is equal to 1. So at x is equal to 1, left-hand side gives me 3 is equal to a times, well, x is equal to 1, so it's a times 3, or 3a. There's a 0 coming out of this, and so a is equal to 1. And then to bring everything back as I need it, we have the original expression 3x over x minus 1, x plus 2 is equal to a, which was 1 over x minus 1, and then b was 2, so plus 2 over x plus 2. One of the advantages coming out of this is I can now graph the expression on the right hand side a lot more easily than I could graph the expression on the left hand side. So if I just want to graph it, I take standard axis. So I could see from the left or from the right that at x is equal to 1 or x is equal to minus 2, we should have some asymptotes. So x is equal to 1 here, x is equal to minus 2 over here. The function is not going to be defined at either point. And indeed, as we get close to either point, one of these two terms will go to plus or minus infinity. So in this case, as I get close to x is equal to 1, this term here will go to plus or minus infinity. The other thing to observe is that because this is a proper rational function, as x gets large, either towards plus infinity or minus infinity, this expression goes to 0. Indeed, both of these expressions go to 0. So we expect to see asymptotic behavior tending to just the x-axis on the extreme left and right. Focusing just on the point x is equal to 1 for the moment, if I approach it from above, so something bigger than 1 minus 1, I get something positive. So it will end up going off to infinity and then going off to 0 on the right. If I have something that's just a bit less than 1, this expression is negative, and so it's coming up from minus infinity. The other thing I can note here on the left-hand side, it's actually more transparent to see on this part of the expression. This function is 0 when 3x is 0. So it will pass through the x-axis at that point, and I can do a very similar analysis, and I find that it goes off to plus infinity here, and it comes from minus infinity, though I am going right to left, and tends to 0 as I go to the left. So that was the first example. The second example, the solution that I'm looking for, because I have a linear factor which is repeated, we have a constant divided by the linear factor, and I have to keep increasing the exponent here and having a constant above until I've exhausted the number of times that it repeats. So another constant b divided by x minus 1 squared. That's as far as I need to go. If that was a cubic, I would have another term, but it's quadratic, so I stop. The next is an irreducible quadratic, and so I take a general polynomial of lower degree, so that's cx plus d, and divide it by x squared plus x plus 1. And that was only to exponent 1, but essentially that's all that I have left. So I can multiply this out as I did before and equate the numerators. I'm not inclined to write that out in full detail, but rather to see where I'm going. We know that we have 2x squared plus 4 on the left, and I'm just going to go straight ahead and write down the numerator of the right hand side as it would be if I multiplied it out. So in order to make this over the common denominator, as I have on the left, I need to multiply top and bottom by x minus 1 times this irreducible quadratic. So I do that, but I ignore the bottom. So it's a times x minus 1, x squared plus x plus 1. Then the second term, we have a b. We already have the x minus 1 squared, so we just need to multiply by the quadratic. So that's x squared plus x plus 1. And then finally, we have the cx plus d. We already have the quadratic, so we multiply top and bottom by x minus 1 squared. In difference to the previous case, I don't really have a good choice of values for x beyond x is equal to 1. So I can substitute that, and then the first term vanishes, as does the third, and I'm left with just b. So we can do that, but then I'm going to have a problem in terms of finding other values. So let's just take what I can at the moment. So I take at x is equal to 1. The left-hand side becomes 6, and the right-hand side becomes 0 plus 3b plus 0. So we get that b is equal to 2. So quite a simple thing to work out. So I don't have any other nice values of x. If I put in any other value of x, then I'm going to get an expression which involves a, b, c, and d. And although I can solve it from there, it becomes a little bit messy, so I'd rather not. What I can do instead is look at, say, the highest degree terms that are going to occur. So on the right hand side, we're going to have a cubic coming up from the first product, quadratic from the second, and cubic from the third, the x times an x squared coming from here. So we look at the coefficient of x cubed. On the left hand side, that coefficient is 0 because we don't see any x cubes. On the right hand side, there's only one way I can get it from this term, a times x squared. So it's just a. We can't get cubed from here. And on this side, it's cx times x times x. We'll get a cx cubed over here. So the coefficient is c. And that tells me that a and c are the same quantities, but they're negatives of each other. It's not another value, but it gets me closer to understanding how the values are related. And certainly it's a linear equation with only 2 unknowns, which is a little bit nicer than having all 4 all at once. So the next thing is the coefficient, looking at the other extreme, the coefficient of x to the power of 0. I can see that as the constant term, or if we let x is equal to 0, then we're going to get the same thing. So all of these are the same. In other words, the constant term, we're letting x is equal to 0. The left-hand side, we get 4. The right-hand side, it will be initially minus a. Then it will be b. although I already know that b is equal to 2, so I'll just write down my 2. And then finally the constant term is d times 1, so we get plus d. So in total, that lets me relate a and d. A is equal to d minus 2. Those are all relatively simple to work out. Unfortunately, that's about all that I have in terms of simple things to work with. So at this point, if I can consider, say, the coefficient of x or the coefficient of x squared, I'm going to get contributions from most of these. If I consider evaluation at some other point, again, I'm going to get a contribution from all of the unknowns. So instead of looking at, say, a linear coefficient, I'm going to consider when x is equal to minus 1. Now the reason I'm considering minus 1, if I consider this irreducible quadratic, x squared is 1 at that point, minus 1, so those will just go away, so I'm left with 1. So this factor, it doesn't become 0, it doesn't trivialize everything, but nevertheless it becomes something simple, and so I consider the other factor x minus 1, which is at that point just minus 2. So it's not too difficult to work with. X is equal to minus 1, left hand side will give me again 6, 2 plus 4. The right hand side will give me minus 2a, because that irreducible quadratic is 1, plus b, so again plus 2. From the last term, the x minus 1 will be minus 2, so that will give me a 4 times d minus c. Okay, so now it's a matter of eliminating down into one unknown and then unraveling the whole system. So I have a nice way of replacing a is minus c, so I can do that. I would like then to write d in terms of c. If everything is going to be written in terms of c, for example, it's just the one I'm picking. So if a is minus c, a, which is also d minus 2, is minus c. So what I can get from that is d is 2 minus c. So d is 2 minus c and a is minus c. So bringing that 2 over, I'll just have a 4. Minus 2a, well, if a is minus c, that's 2c. And plus 4 times, if d is 2 minus c, then that's 2 minus c minus c. And so now I have a linear expression involving only one unknown. 4 is equal to, I'll just multiply this out, that's 8. So that's minus 2c times 4, so that's minus 8c. So rearranging, we'll have a 6c is equal to 4, and so c is equal to 2 over 3. Now c is equal to 2 over 3, I can easily relate that to a, so a is minus 2 over 3, and similarly d is 2 minus c, d 2 minus c, or 2 minus 2/3, so that will be 4/3. And so that gives me all the information that I need. I'll put it back together and then I'll resume from there. So on the left hand side, this was the original expression, a, which was a over x minus 1, so a is minus 2 over 3. So I'm bringing here, rather than saying a rational number divided by something, I'm writing it as a proper rational expression. And then b was 2, and again I'm dividing by the 3 that's in the c and d, and we get 2x plus 4 in the numerator. So that gives us the partial fraction decomposition. Now if I try to graph it, first thing to note might be that the function is never 0, 2x squared plus 4 is never 0, and there will be a problem with defining the function at x is equal to 1, but that's it. Everything else will go to 0 because it's a proper rational function. Go to 0 as x gets to plus or minus infinity. So knowing that everything is always positive, I will remain essentially in the upper half plane. We have an asymptote at x is equal to 1. This is the only place where I have an asymptote. And in the other example, we saw essentially the function will go off to infinity, and then it would come back almost as if it had gone around a circle and come back from minus infinity. That's not going to happen here. For one thing, the function is always positive. So as I approach from above, I'm going to get two different expressions which are going off to plus or minus infinity. The first one here is going to go to minus infinity, because from above, x minus 1 will be positive. So all of this will go to minus infinity. And that will fight with this term. Overall, this will go to plus infinity. But actually, it will go to plus infinity much more quickly, because for values of x minus 1, which are close to 0, once I square those, they're going to be even closer to 0. So this will win out, and overall it will go to infinity, but this will slightly slow it down. This will mean it doesn't go to infinity quite as quickly as it would otherwise, but eventually it will just tend off to infinity anyway. It will look something perhaps like this, and it goes to 0 as I go to the right. Then on the left, since x minus 1 will now be negative for values of x beneath 1, this whole thing will go to infinity, and for just the same reason, this will also go to infinity. So this will almost go to infinity at an accelerated pace. And so the graph will actually look a little bit taller, as if it's heading off to infinity faster on the left-hand side. This is only an approximate graph, but without plotting any data points whatsoever, I can analyze both of these. One thing to note, I've ignored this one, and pretty much for good reason. It will tell me things about the shape of the curve once I want to get into fine information, but just looking at the behavior around this asymptote, then this is approximately 6 divided by 9. It's just some little extra constant, and it doesn't make any difference when I go to infinity. It just falls away in whatever noise in my graph. One of the most important things is in being able to write down the proper type of expansion that you want, and then it's just some linear algebra after that, but having a strategy there can really help.